Alright, so this is the 8th lecture. We're gonna discover some properties of compact sets. So first, let's look at this one. So if k is subset of y and subset of x, then we know that k is compact relative to x if and only if k is compact relative to y. So they're equivalent. Whenever you're compact in this, then you're compact this. You're compact in here, then you're compact in here. Alright, so let's just prove it. So we should prove this direction if k compact in x, then we let V alpha be a collection of open sets in Y. So V alpha is open in Y such that it covers K, right? So it covers K. Oops. V alpha. Alright. Okay. Now, while we know that V alpha, they're open in Y, then by the last theorem we proved, which means that V alpha is equal to Y intersect with some G alpha, where G alpha open in X, right? It's open in X by the last theorem. So now, by this statement, then is equal to, we substitute in, right? We substitute in, and since all these sets, they're a subset of G alpha, right? So a subset of G alpha. Well, look what we have. An open cover of K. Then we know K is compact in X. So we know that K is a subset of alpha 1 union with G alpha n, right? By K is compact. And also we know K is subset of Y. So we have K is in all these finite subcovers intersect with Y. It's like followed by definition, right? K is in here, also in here, then it's in the intersection. Well, this intersect Y is equal to G alpha I intersect Y. Well, look what we have now. Look at this. We just substitute in. Then we know that. So K is compact in Y. Right? Now I prove the converse. We shall prove the converse, which means that if K is compact in Y, then compact in X. Well, K compact in X and compact in Y, then first we let this be collection of open sets in X such that it covers K. It covers K, open cover of K in X. Alright, now we put each V alpha equals to Y intersect with every single G alpha. Then, since we know that K is a subset of Y, right? And also K is a subset of all these, then we know that we combine this and this, right? We have K is a subset of intersects Y, isn't it? And then again, G alpha intersects Y, which is equal to V alpha. Now while K is compact in Y, compact in Y, then we have K, some finite subcover. Oh, wait a second. Yeah. So we have G alpha are open sets and X covers K, right? And so we put V alpha equals to this, some open and Y, and this is open cover of K and Y. Since it's compact, we have a finite subcover. Well, of course, each V alpha is a subset. It's a subset of G alpha, right? Because if you're in V alpha, you must be in G alpha and Y, right? Now we're good. K is compact Y. Then K compact. K is compact in X. Right? Now we're done with this one. Now we should show that compact sets are closed. Well, if you want to show a set is closed, we can show that suffices to show that K complement is open. Right? Okay. So here's the picture. So the picture is that, okay, you have K here, right? We want to show like all these things outside are K. Everything outside is K complement. This is K. All right. So what we want to do. So now if we pick a point, which we want to show that every point in K complement has a neighborhood that is contained in K complement, right? So if we let P is in X such that P is not in K. So for each Q and K, so we have here's P, and we have say Q here, right? We construct something, right? So how the construction works? So the distance between P and Q, and then we take their midpoint. So here's a neighborhood, and here's another neighborhood, right? We do this. You're gonna see what's going on. So we construct N which EQ you have a radius with what? With the radius is less than 1/2 the distance of P and Q. We want this. Okay? So now we know. Now we have, well, of course, each Q and K, the neighborhood of our QQ, open cover of K, right? Cover of K. This is obvious, like neighborhoods are open. You take L the points, you take the neighborhood. Of course, their union covers K, right? Okay, so now we know that K is compact. So we know that K is in some finite cover. It's in some finite cover. Right? Okay. Since K is compact. Now, what we have now is that, okay, for each P, for the point P, notice for the point P, for point P, right? For point P, we have that, okay, so you take their midpoint, and the radius is less than the midpoint. This radius, if we consider another radius less than like the midpoint, then the intersection is empty set, right? For each P, we have N RQ Q intersects N RQ P is empty. Well, this intuitively makes sense, but I want to prove it rigorously. It makes sense in the picture, but if we'll use the definitions to prove it. So if y, so say if we have a set A is in this, right? Then we know that A is in both of them, right? Which means that the distance between A, RQ is less than, A between A and Q is less than RQ. Also, the distance between A and P is less than RQ, right? Now, so we have distance of P and Q. We use the triangle inequality. Well, each RQ is less than this, right? So 2 times 1/2 dPQ. Well, this becomes PQ. Now here's the contradiction. We have this less than equal to this. Not even less than equal to, strictly less than this. A contradiction, right? Okay. If this intersection is empty, now we take the minimum. We take the minimum radius. Right, we take the minimum radius. Then we have QI is empty for all I. Well, of course, this is true. Why? Because we know that R is less than or equal to RQI. And we know that NRQI is empty. Well, this set is a subset of this. Well, if this is empty, of course this is also empty. It's like straightforward. I'm just illustrating a bit more here. Right, so what we have now is that, well, all these is a finite subcover of K, right? While this neighborhood of P intersects all of them it gives you empty set. So we have NRP intersects K. Oh, this is a bit too fast. Yeah, I know that makes sense, but if you want to prove it like rigorously. NRP. Well, this is a subset of the finite subcover. Right? This intersects NRP by definition subcover, which is equal to this union, right? Which is a union of empty sets. Well, this intersects this is empty, which means that NRP is contained in the complement. And we're done, since KC is open. Okay, so this theorem shows that, well, compact sets are closed, right? And now we have a next theorem which states that closed subset of compact sets are compact. So you have a compact sets, say F subset of K, metric space X, F closed, right? And K is compact. Now, first we don't let V alpha be open cover. Pen cover of F. Right, so say that we have a compact set K, and this is K, this is F, and then we have open covers of F, right? Well, this V alpha, it covers F, but we cannot guarantee that it covers K, right? But if we consider the union, well, this covers F. If we take this union with F complement, right? If you take this union with F complement, which is all other those sets, then of course it covers K, right? Union of FC. Well, this covers K, but is this an open cover of K? Yes. Why? F closed, F complement is open. Open cover of K. K is compact. So we have finite subcover, right? And union with F complement. Well, this thing, it might be here. It might be here. We don't know. But what we know is that, well, F is a subset of K, right? So F complements are removed, then covers F. We want to find a subcover of F, right? Yeah, of course this covers K, right? And also this covers K, and F is a subset of K, right? So this covers F, but with this being removed, it doesn't matter, right? Because the intersection is empty. So even though it's removed, this still covers F, which is a finite subcover of F. Well, open subcover has a finite subcover. F is compact. Okay, so now we have a corollary. F is closed, K is compact, then their intersection. I'll just let the music go. This is my wallpaper. So F is closed, K is compact, then their intersection is compact. Okay, so F closed. We prove it. F closed, K compact. Then we have that F intersects K is closed because finite intersection, like arbitrary intersection of closed sets are closed, so F compact sets are closed. We proved this, right? Compact sets are closed. So this is closed. Well, this is a subset of K. Closed subset of compact set is compact. So this is compact. And then we have next theorem. So what it states that, okay, you have an arbitrary collection of compact sets and such that all the finite intersection is non-empty. If all finite intersection is non-empty, then the whole intersection is non-empty. Well, of course, we can do it with contradiction, right? Suppose for a contradiction such that this is empty. Well, if this is empty, then their complement is the whole space, right? And then for something like this, we use De Morgan's law. De Morgan's law. Right? Okay, we have this. Now we fix F, K of alpha naught is some collection, right? Well, of course we know that this open cover of K of alpha naught, because compact sets are closed and the complement is open, right? So it covers K naught, and also K alpha naught. Also, K alpha naught is compact. So we have a finite subcover. You see, like, we use the compact property so many times. Well, okay. Now here's the magic. So K alpha naught is a subset of this. So this is a subset of this. Well, if you take the intersection of this and the complement of this, it should be empty. So if A is subset of B, A intersects B. Right? Here's the magic. Oof, the whole thing is empty, right? So now we have K of alpha naught intersect. Well, you use De Morgan's law again. Right? De Morgan's law. Well, this, the double complement, which is itself. Okay. Now, what is this? This whole thing is a finite, like finite intersection, right? And it's empty. But it says that every finite subcollection, intersection and any finite subcollection is non-empty. But we have something empty. Why? Because we assume the whole thing is empty, which is a contradiction. Now I have a corollary. So a sequence of compact sets, sets that are nested, then it's not empty. Well, this is simple because this already implies like a finite subcover is not empty, right? And you just use it. Simple. This is simple because in form of this, any finite intersection is of course non-empty, right? Well, this theorem is quite interesting. It says that like an infinite subset of a compact set has a limit point. Well, how should we approach? We always do it by contradiction, right? Suppose for a contradiction that E has no limit point in K, which means that for any Q and K, Q is not limit point, right? If Q is not limit point, then there exists a neighborhood around Q such that intersects E is, this is at most, right? Because we know that the puncture neighborhood is 0, and that if you include the center intersects Z, it is at most the singleton set Q itself. Clear? Okay. While if you take every point in K, you take all such neighborhood, of course it covers E, right? Because E is a subset of K, right? It of course covers E because every Q and K includes every Q and E, and every Q and E you generate a neighborhood, then it covers E, right? Trivial. But no finite subcover. But no finite subcover of E. Well, why? Why no finite subcover covers E? So, if so, then since E is infinite subset, right? You have a finite. I'm not gonna write it. I'm gonna speak loud. So, E is infinite subset, and if you have a finite set that covers E, which means that at least one of the neighborhoods must have infinite many elements, right? Because if you're finite subcover, then their union must be infinite. One set must have infinite elements. Else, if they all have finite elements, then their union is finite. It can't cover E because E is infinite. So, if one has infinite many elements, but we know that each neighborhood contains at most one point in E, right? So it's a contradiction. So no finite subcover of E. So E is not compact. Well, we're just saying that like there exists an open cover such that it has no finite subcover, which is the negation of the statement that for any open subcover there exists a finite subcover. So E is not compact. compact, right? E is not compact, right? Which means that the negation of this infinite subset of a compact set K. Has no such subcover, so E is not compact. E is not compact. Subset. If E is not even compact, well, if it can't even cover E, how can it cover K? If it can't cover E, how can it cover K? Right? So it should actually be K is not compact. Right? We're good.